Okay, we'll go ahead and get started. We have 12 participants right now. So I would think that if, the rest of the crew can sign in as we start presenting, but since we're recording, we can make sure to send it to all participants as well. So we are going to get started. My name is Nikki Giordano. I am the Executive Officer with the NoCo HBA, the Northern Colorado Home Builders Association. And I'd like to welcome you all to our 6-part webinar series on construction workforce training. I'd like to thank Robby Schwarz with BUILDTank for hosting this course. And this webinar starts today and runs through August 14th. Obviously, there's different topics each week on Friday mornings. I believe they all start at 8 a.m. Some do run, most run for an hour. There are a couple that run for 2. Please make sure to check our website at nocohba.com for the list of the courses. And we will be here every morning, like I said, or every Friday morning at 8 a.m. to do these. So please make sure to get signed up and we'll send you the Zoom information. I'd like to thank Xcel Energy for sponsoring this series, as well as the City of Fort Collins to make this possible. Obviously, this course is at no charge to all of you. So we really appreciate the partnership from BUILDTank, Xcel Energy, and the City of Fort Collins. Now we'll go ahead and get started, and I'd like to introduce Brad Smith. He's the Energy Code Compliance Specialist with the City of Fort Collins. So Brad, go ahead and take it away.
Yeah, thanks, Nikki, and hello, everybody. So thanks again to NoCo HBA for kind of pulling us in to help promote this series. Nikki kind of gave an introduction to myself and my position with the city. I also, without taking up too much time and letting Robby get on with his program, I do want to mention something to everybody, and that is that the City of Fort Collins is kind of right in the middle of work on our climate plan, or what we call our climate future. We're soliciting outreach and community engagement at this time to kind of help us inform the future of what our climate looks like within the city, and a lot of that includes building and topics such as renewable energy and building efficiency. So I want to pass along and share a link and just encourage people, if you have a moment and would like to give us some feedback, participate in any of our workshops, we would certainly welcome that and encourage that from any of those willing to do so. We do have a link, and I'll share that with you now, and I'll also put that in the chat, but the link is ourcity.fcgov.com/our-climate-future. And on this page, on the right-hand side of the page, you can find links to share your ideas and sign up for workshops. So that being said, I'll just jump right into Robby because I'm sure he's ready to go. I want to just do a quick introduction to Robby and just kind of let him roll with it. So those that don't know Robby, he's been kind of a foundation in this industry and in Colorado for a number of years. He's recently founded BUILDTank Incorporated. I'm reading off of his introduction or bio here. The mission of BUILDTank is to use what we learn by applying building science in the field to affect meaningful change in the construction industry. So I think that fits in good with what city's thinking is on the future. So I'm happy to have Robby here and present. So I'll turn it over to you now, Robby.
Great, thank you very much, Brad. Thank you everyone for taking part. I'm going to stop my video as well so that we can concentrate on the screen here. Today we are looking at an introduction to building science. And before we get started, I wanted to give a great shout out and thank you to the Northern Colorado HBA, the City of Fort Collins, and Xcel Energy. Thank you so much for supporting this webinar series. It's greatly appreciated, and I'm hopeful that everybody will gain something from this series to move us forward here. I will be staying on and answering questions at the end. So if you do have any questions, there's a question and answer pane in the Zoom profile, I believe at the bottom of your screen. So please type in questions there, but we won't get to questions until the end. Our plan today is to, again, talk about building science and give you a primer with regards to building science, systems thinking, how it is integrated with code today, and then talking about the applied building science in itself. To begin with, we want to have an idea of what our industry is about. And this is a great quote from an organization called EBA, or the Energy Environmental Building Alliance. They say residential construction is a complex operation, including thousands of processes by dozens of industries, bringing together hundreds of components and subsystems into a house. And what we see from this quote is how complex our industry really is. That complexity, though, is tainted a little bit by the notion that we've been building or stick framing houses for quite some time. The thing that has really changed, though, is the number of people that are involved in the process. We see that back in the 1870s here in Nebraska, you know, potentially a small family business or a group of farmers and people coming together in a community were taking a house literally from foundation through finished carpentry. Today, through some research that the National Home Builders Association has done, we see that, you know, upwards of 300 people are touching a house today. And the big thing about those 300 people is that they've become specialized. Each person is doing a specific thing in the house, and very few of the people that are involved in the construction process really understand the totality of taking it from foundation through finished carpentry. We have an insulator, we have a framer, we have a plumber, we have an HVAC contractor, an electrician, all these different subsets that are coming in and doing their one particular component, and potentially within that they're subdividing even more. You know, you might have that electrician and 10 guys coming into a home, one drilling the holes, one pulling wire, one putting in boxes, one putting the wire into the boxes, another stripping it, you know, all so forth and so on. So we really need to understand this idea of systems thinking there. We also have this new, relatively new issue that's facing our industry, and that's with regards to labor. And that is one of the reasons why we're starting to specialize more. But we saw during the last recession that a number of folks left our industry, and a number of other folks are at kind of retirement age. So we need to figure out how do we bring people into our industry, people that are conscious and understanding this more holistic approach to building our houses, so that we move to houses that actually perform and work. These times have changed, and the expectations of our houses have changed pretty dramatically. These pictures show houses, you know, from the past in the early 1900s, right next to a modern day house, or, you know, in parts of Denver where I am, we're seeing whole blocks being scraped and new housing being built on those blocks. But what we're also seeing is that the thing that's driving this kind of change and newness in our housing is people's expectation of their housing. If we look at those expectations, things like comfort and durability and aesthetic beauty, and we focus maybe on comfort, we can get an idea of how these expectations have really changed the way that we're building. So for example, in the picture in the lower right-hand corner, we have a house that was built in the early 1900s on the left, and a modern house built in 2020 on the right here. And if we look at comfort, we can really see that comfort expectations are fundamentally different from 1900 to our modern day here. We've got a house in the 1900s where our grandparents might have lived, and they probably were willing to supplement what the house couldn't do. In essence, they were willing to put on a sweater in the wintertime. Potentially they had to shovel some coal or put some wood on a fire to get comfortable in that house. In today's world, we're not willing to do that. We basically want to be able to walk around in our underwear from room to room and floor to floor and be quote unquote comfortable. And those fundamental change in expectations of our houses have changed the way that we construct our houses. So we're adding complex heating systems, we're tightening up the building envelope, we're adding insulation systems, and that's relatively new. So we're still trying to figure out how to do this in the best way possible to get a house that will last. You know, insulation, for example, really wasn't mainstream being installed into our houses until the early 70s. So that wasn't that long ago, really. So this notion of applied building science and systems thinking has kind of fundamentally changed the way that we're thinking about how housing goes together. And we're seeing that being adopted by the codes that we're working with to build our houses today. So it's a good idea to spend some time to introduce ourselves to applied building science and systems thinking and have that base understanding as we move forward here. So applied building science is really looking at a lot of different components and how we put these components into our houses, from water saving to energy efficiency to comfort, all these different things going together in our thermal envelopes, in our designs, in our expectations of our houses. If we break it down though into its core, we're really talking about how do we understand airflow, heat flow, and moisture flow in our houses. These are the things that we're trying to gain control and predictability of in a more holistic and scientific way so that we can fundamentally meet the core expectations that people have of their homes here. So to begin with, this approach is revolving around a relatively new concept. You know, in the last 20 or 30 years, this idea of systems thinking, or this holistic approach rather than a component approach of looking at how we're putting our houses together. So systems thinking revolves around this word synergy, which means that two or more things are coming together to achieve something greater than what could be achieved alone or by themselves. And what I like to say is that these core expectations that we have of our housing really can't be achieved if we aren't taking a synergistic approach in how we build our houses here. And that synergistic approach can be exemplified, you know, in a simple, relatively simple example here. You know, we have two components in our houses. We might put insulation and an air barrier system together, and we think we get one outcome of that. We're controlling heat flow in our houses. But the reality is that these two things are coming together, and we're not only getting a better control of heat flow, but we're also getting better control of airflow in our houses. We're getting better control of moisture flow in our houses. And we're also getting better indoor air quality inside of our houses. So these two things that are coming together are achieving way more than we might think about. You think about putting a piece of duct and a fan together. Those two things come together. Well, we're getting airflow, but we're getting moisture control. We're getting better indoor air quality again. So a lot of things that we put together synergistically work together to create the expectations that we have in our houses. And you know, one of those expectations is long-term durability. We want that house to last a long time. So really, when we're talking about control and predictability of heat flow, moisture flow, and thermal flow, we're really talking about durability and how long houses will last over time to meet those other core expectations that people have. From a building systems integration perspective, we need to figure out how we take the structure of our homes, the systems in our homes, and the enclosure of our homes, and how do we do that in a systematic building science applied manner? And how do we do that in a particular climate that we're living in with whatever occupants are inside that house? All these things are coming together to create problems for us. And you know, the systems and structure and closure and climate, those things are things that we can wrap our hands around. But the people become the big wild card. They are the things that are going to turn our houses upside down. Those are the things that we don't have control over. We might be building a house for a retired couple, and the contract falls through, and a family of 5 comes and wants to buy that house. You know, as a builder, I'm not going to say, I'm sorry, this house is designed for a retired couple, therefore you can't buy it. Obviously, I'm going to try and sell that house, but that family of 5 is going to live in that house fundamentally differently than that retired couple. And I need to be able to build a house that is going to be able to meet the expectations of whoever's living in that house, and understand what they care about, understand what their expectations are, understand, you know, potentially the strange things they're going to do to that house over time, so that we can take that into account and continue to build a house that will last over time, that will be comfortable, that will be energy efficient, that will meet the intent of the code and work for everybody. So in essence, we're trying to figure out, how do we take people out of the equation and build a house that lasts in whatever climate we're building that house in. So the code starts talking about the climate part of this equation using this climate map. And this climate map, you'll see climate zone 5, which we're in the Front Range of Colorado. It stretches across the country. And then there's this bold line that goes down the middle that divides the dry portion of the country from the moist portion of the country. So we have kind of similar things that we're trying to do with our houses from a code perspective in climate zone 5, but we're going to tweak them slightly in our dry climates versus our moist climates, so that we have houses that, again, will achieve that long-term durability that we're going to achieve. So the macro climate is super important to understand. In Colorado, we've got probably the most climate zones of almost any other state. So if you're not only building here on the Front Range, you need to understand where you're going to place that house. If you're going up into the mountains, are you moving into climate zone 6 or 7 or potentially 8? Or if you're going somewhere else, you might hit climate zone 4 there as well. And again, you're going to be asked to do something slightly different there, but it's all revolving around this notion of systems thinking and applied building science from that macro level. But we also have micro climates that are inside our houses. Microclimates can be exemplified by this oasis that's in the middle of the desert. So in the middle of the desert, this palm tree is growing, and what's the factor that causes that pine or that palm tree to grow? Well, it's moisture. Moisture is the thing that really drives these microclimates inside of our houses. So again, in order to control the environment, we need to be able to control the temperature and humidity and the moisture that's there, so we have more consistency and better indoor air quality there. Otherwise, things like this might happen inside of our houses, and obviously we don't want that type of mold growing in our houses. So to get that control and predictability in our houses, we've tightened them up. We've added insulation systems and mechanical systems and ventilation systems, and we need to figure out the integration of these things, the synergy that comes from putting these things together to achieve our goal. And our goal might just be, I don't want mold in my house. I want my house to last over time. Well, if we have just that simple goal in our houses, well, tightening our houses, insulating our houses, mechanical systems, ventilation systems, the integration of these things are what we need. But we might have other goals. We might have to meet the 2018 IECC. We might have to meet an Energy Star program or a building program through the Department of Energy Zero Energy Ready Homes program. These other goals are goals that builders are trying to achieve all the time. The big thing about these goals, however, is that we need to share these goals with all our trade partners. We need to make sure that our trade partners understand what the goal of the house is, what code they're being billed to at a minimum, so that they can successfully build a house to meet the expectations that we have. Now, the IECC begins to think about building science and systems thinking when we start talking about the thermal envelope and the different control layers of the thermal envelope there. But really, the IECC brings it down into even simplifies it more, I would say. And that is by trying to clearly depict the thermal envelope on our drawings here. Now, the building thermal envelope is defined in the code as basically assembly of things. Now, this assembly of things can be broken down into two primary components that create that building thermal envelope. And that would be our insulation systems and our air barrier systems. And the continuity of those air barrier and thermal barrier systems around our house to separate conditioned space from unconditioned space. And that's what needs to be depicted on the building thermal envelope, because a lot of times it's not easy to decipher this out in the field. So we have this building thermal envelope in our houses, and it's defining this separation between conditioned space and unconditioned space. And sometimes it's awfully difficult to determine where that envelope is going to be. And so the code is helping us determine how do we add supplemental air barrier systems into our homes so that we have that continuity between the air barrier systems and the thermal barrier systems in our houses there. Sometimes we'll see that it's pretty difficult to achieve that, and therefore we need to get some help from people, either third parties or code inspection agencies that will come out. And basically, as a builder, you're going to say, this is where I want my building envelope to be. Well, an inspector can help you achieve that and help you figure out how to make that continuity happen. So the code moves forward and it talks about this continuity and that we need a continuous air barrier and thermal barrier all the way around our house. And again, it talks about these things as an assembly of different products that come together to achieve that air barrier system around our house. In its simplest form, the air barrier system of our house can be thought about as the interior drywall and the continuity of the interior drywall in our houses. So you'll see often in sections of the code where we don't have drywall in contact with the thermal insulation in our houses, the code will be asking us to add a supplemental air barrier in the system there. For example, behind a tub on an exterior wall. Well, that tub isn't necessarily the air barrier. We might have to add a piece of thermoply or OSB or something to get that air barrier connection between the interior of the house and the thermal barrier, the insulation of that house. In the same way, on the exterior side, the exterior sheathing is our primary air barrier on the outside of our houses. So often in construction, we think of one clear air barrier system in our houses when the reality is that the whole assembly can and often helps create the continuity of that air barrier all the way around our house there. And so that brings up the question of, what's the house wrap? I've always thought the house wrap was the air barrier of the system. Well, really the exterior sheathing is our primary air barrier. The house wrap might be a supplemental air barrier, but the house wrap's true reason for existence, I guess, is to be this drainage plane, is to be the part of the house where water's going to hit, because water's going to bypass our siding. Water needs to be able to hit a plane, a control layer that could be this drainage plane that will drain the water down and out and away from our houses ultimately. So the function of the air barrier system is to help us enclose the insulation, especially if it's a fibrous insulation. And so you're going to hear more and more out there this notion of six-sided enclosed cavities when we're talking about cavity insulation in floors and walls. And then to help gain control of air, and our thermal and moisture control in our houses. So the air barrier system and the thermal barrier system working together in continuity all the way around our house gives us better control and predictability of air, heat, and moisture in our houses there. And the code, again, begins to help us execute this in the field through this table in the code. So this table in the 2015 and 2018 IECC, the insulation and air barrier installation table, breaks down the house into different components, different things you need to do from an air barrier perspective and from an insulation installation perspective there. So we need to understand this table. We'll be looking at this table later on in this series in more depth. This is just an example of the air barrier that's called out in this table behind a tub, for example, on an exterior wall. So again, we have to abide by manufacturer instructions, but we also need to abide by what is called out as a mandatory requirement in the code as well. And what it ultimately gets us to from an air barrier perspective are these 5 key attributes. We need continuity, strength, durability, stiffness, and impermeability of the air barrier systems that we're installing in our houses. So we have to understand that fibrous insulation is not an air barrier system. It's air permeable. It allows air to move through it. So we need to pick things like thermoply, OSB, drywall, foam sheathing, these rigid air barrier systems to create the continuity around our houses and those air barrier around our houses, because those are the things that last over time of our houses and have the strength and continuity that can work and actually function in our houses. So applied building science, again, in the code, let's break down thermal flow, moisture flow, and heat flow. We're going to start with thermal flow in our houses and talk about the different components here. So heat flow, the thing to know about heat is that heat always moves from higher concentrations to lower concentrations, or in essence from warm to cold, and never in the other direction unless you add additional energy to the equation here. It's based off of these laws of thermodynamics, where it says that energy can't be created or destroyed. Energy moves or changes forms, and there might be some waste there, but the energy heat is this transfer mechanism between different components, always from higher concentrations to lower concentrations. But again, there might be some waste in that process. And we can see that if we look at a furnace, for example. So if I have a furnace and the energy in equals the energy out plus some waste, we can see if I had 100,000 BTU and it was 90% efficient, then 90,000 BTUs would go into heating that house, and 10,000 BTUs would be waste that's going up the flue. Now that waste heat isn't beneficial to the house, but it's not destroyed heat. That energy is still out there. It's going into the atmosphere. It's going into the weather patterns, for example. It's just this notion that energy isn't created or destroyed. It just changes forms. And one of those forms might be a little bit wasteful there. So ultimately, from an energy efficiency perspective, we're trying to limit that waste as much as we can here. The second law says that heat moves from high temperature regions to low temperature regions, as I said before, in essence from hot to cold or from higher concentrations to lower concentrations. It never flows in the other direction unless you add additional energy. And as we said, there is some waste, so there's no such thing right now as 100% complete reaction there. So there is some energy loss, and energy is going through this transfer process from one object to another object, or from one state to another state here. So temperature is one of these things that we need to understand. This is the heat. It's heat in the form of energy. It's heat as measured and how energy is transferred from one system or body to another. So if, for example, the heat in this body of this dog is moving from the body of the dog into the ice cube to actually cool that dog down. It's not in the other direction there. Temperature is also a measurement of the internal energy of the system. This is the measurement of how fast molecules are moving inside that system. This gives us the ability to measure the heat in a thermometer. As those molecules move, the thermometer goes up there. So there's this measurement quality in heat as well. Heat is transferred in this exchange between physical objects here. But things don't have to necessarily be hot to have energy. And this is how we understand a heat pump working, for example, or really a heat pump. If we're trying to heat a house in the middle of winter using a heat pump, for example, it's baffling to our mind that we can get energy out of super cold air. And now we're getting energy out of air that's below freezing, which is really amazing that can happen. And it's all because of the physics that let us know that there's still energy in cold air that can be moved into the house to actually heat that house. So that's part of the energy transfer mechanism that we were talking about here. which makes us need to understand this notion of delta T, or the temperature difference between different locations. So if I have a 68-degree interior temperature inside this house and a 10-degree outside, I have a delta T, or temperature difference across my building thermal envelope of 58 degrees. That's going to help me understand the direction of heat flow from inside my house to outside my house. Generally, this is happening in Colorado in the wintertime, and in the summertime, it switches so that we have more heat outside than we have inside, and the energy is trying to move from outside to inside our houses there. And therefore, we're trying to create mechanical systems that can supplement the heat loss or heat gain that we might be having in our assemblies. This notion of delta T also drive the interior design conditions that the IECC makes on our houses. So it says for load calculations, we shall have a maximum of 72 degrees Fahrenheit for heating and a minimum of 75 for cooling. So that would be our interior design conditions. And then if a jurisdiction doesn't set that outside design temperature, you would go to the ASHRAE tables to get that. But some jurisdictions actually set that outside design temperature as well to better size our heating and cooling systems in our houses there. So just to summarize here again a little bit, the flow of energy is from hot to cold, or from higher concentrations to lower concentrations. And the higher the delta T, the greater the heat and air, or the more the heat and air want to escape or enter into our buildings here. So delta T, again, is a good concept to have an understanding of from this heat flow perspective here. The last two things we're going to talk about are two types of heat and some energy principles here, because you need to have just a concept of sensible heat. Sensible heat is heat that's able to be sensed by that thermometer, heat that's able to be absorbed or released by a substance. This is the energy that's ultimately described by heat load calculation, the energy that's going in and out of our buildings. And then the next one is latent energy, and this is the energy that's released or absorbed by a substance during its change in phase. So if we're going from a solid ice cube to liquid water to liquid or to vapor water in its vapor state, energy is being released at each of those times, or being absorbed depending on the direction that it's going there. So latent heat is kind of a swing factor in our design process, especially when we're talking about HVAC systems and designing HVAC systems. And in Colorado, we don't have a large latent heat load in our houses. So we're primarily concentrating on the sensible heat. But you're probably going to come across a notion of latent heat when you're talking to an HVAC contractor. And it's good to have a good, a background and understanding of what they're talking about there. And then the last thing, the two kinds of energy, we have potential energy, which is stored energy in a cord of wood or an ice cube, energy that can flow between objects, from higher concentrations to lower concentrations. And then kinetic energy, this is the energy of motion, atoms or molecules in that, and that's what we're talking about when we're talking about temperature and thermometers out there as well. Energy that's measured in that thermometer would be kinetic energy here. Okay, so that's heat flow, and heat flows through our objects or our homes in three specific ways: by conduction, convection, and radiant energy movement. And let's break these down in a little bit more particular fashion so that we understand them individually, because the reality is that they're working simultaneously in our houses here. If we can understand them individually, we might be able to see, is one a bigger driver than the other? And this is particularly helpful when we're talking about existing homes, if we're trying to diagnose a comfort issue in an existing home, or if we have a warranty issue in a new home potentially as well. But conduction is energy that conducts through a solid object from higher concentrations to lower concentrations. So And generally speaking, in our houses, in the wintertime, we have a higher interior temperature than we do outside of our houses. So the heat flows from inside our house to outside our house, as shown in this picture. And we have certain members of our buildings that transfer heat faster than other members of our buildings. In essence, our studs, our framing, are the weak point in our houses because the R value, or the resistance to the heat flow in our houses, is only about 1 per inch for wood, versus a stud cavity that's blown with fiberglass insulation, for example. You might have an R23. So you're going to have more flow of energy through your framing than you will through your cavities. Our typical 16-inch on-center wall framing is about 25% wood. So it might lead us to consider reducing the wood and going to 24-inch on-center framing, for example, in order to reduce the conductive heat flow and make our house a little bit more efficient. There are other components that are super important to think about from this thermal bridging perspective, where energy can move through our assemblies quickly. And one of those is our slabs. If we do a slab on grade, we must deal with that slab edge component of our house in order to lessen the flow of energy from inside our house to outside our house, and to gain better control of the thermal flow in our homes here. And so there are a variety of different ways you can do that. You can see in figure 2, 3, and 4 here, in order to reduce that heat loss through the slab edge there. It's not an easy detail, but through planning and integration, you can make this happen and happen well. Now, the next way that energy moves in our houses is by convection. This is energy that's moving with a fluid like air or water inside our houses. We can get convective air loops happening inside poorly insulated wall cavities or floor cavities potentially. Generally, wall cavities more because they're taller. As air warms, it moves, and it's warming on the interior side of our assembly. It rises, hits the top plate, and kind of moves itself over to the exterior where it cools. And that's where we start getting this loop effect, where energy is being taken from inside of our houses and moved to the outside of our houses, and in essence bypasses the insulation. So the R value of the insulation, because it's not fully filling the cavity from side to side and top to bottom and front to back, we're allowing convection to happen inside that cavity instead of trapping pockets of air there. So convection happens inside our wall cavities potentially, but also inside of our rooms inside of our houses. So air can be cooling against the window, for example, and fall to the floor. And then as it moves into the interior side of our rooms, it starts warming and rising up to the ceiling and back, creating this loop again inside of our houses. So properly insulated and sealed assemblies help us avoid this convective loop that might be happening inside of our houses, which brings us to an idea of how do we insulate these assemblies properly. Here's an example of a test thermal box that's being demonstrated here. Now we have 4 cavities in this thermal box here. And the idea is to pick which one we think is performing best and what is the R value of the one that's performing best. So we have different cavities here, 19 to 0. And I want you to think right now, which cavity do you think has the R19 bat and which cavity do you think is not insulated? And I think you might be surprised here a little bit, because the R11 bat is in cavity 1, and it has a proper air barrier system. The cavity's been insulated properly, and you can see it's performing the best here. There's the less heat flow moving through that cavity there. Cavity 2 has the R19 bat in it, but there's a pretty substantial gap at the top plate there, and it's not working. The 3rd cavity is an R13. It's installed pretty well, but not perfectly. And the 4th cavity has no insulation in it at all. So what we learned from this is, in essence, is that The R value is definitely important, but really how that R value is installed is even more important there. So to get that reduction in convection and conduction that's happening through that assembly, we need to look not only is the insulation in the cavity, but how has the insulation been installed to actually perform and work properly? And that's really what the code is helping us understand. And over time, especially with help from the city of Fort Collins, we've learned that this notion of is it there and does it work needs to be the focal point of how we inspect homes to demonstrate compliance with the energy codes as they're being instituted now in our jurisdictions. Radiant energy is the last way that energy moves in our houses. This is energy that's flying through open spaces from objects of higher temperature to lower temperatures. The best example, obviously, is from the energy from the sun that's going literally through space to the earth, or a campfire. You've got the energy from that campfire that's moving linearly to you, meaning that it moves in a straight line from that campfire. It hits you and warms you up on your front side, but your backside is cold because the energy isn't able to wrap around your body there. It moves in a straight line there. The big thing to know about radiant energy is that you have to have an air gap. That air gap can be on one side of the assembly or the other side of the assembly, but you have to have an air gap in order for that radiant air barrier or that radiant energy and barrier to actually work. We don't use a lot of radiant barriers here in Colorado. It's generally in a heating dominated climate, but radiant barriers work on for this notion of emissivity. It's a measurement of how much radiant energy a material is able to emit into that assembly there and or retard the movement of energy into our buildings as well here. If you move to a more heating dominant or a cooling dominated climate, you'll need to know a little bit more about radiant barriers, and there's lots of information out there. From a human comfort perspective, we're talking about mean radiant temperature here. So we're talking about this ability of our surroundings to impact our comfort because our body heat can actually radiate from our body to colder surfaces around us or from warm surfaces around us to our body. So it's either moving away from our body or to our body to keep us comfortable or to make us uncomfortable. I don't know if you've heard, but sometimes if you're in a kitchen with a lot of granite countertop and that granite is cold, you can actually be cold while you're cooking your meal because your body heat is radiating to that colder surface of the granite or to the colder surface of a window, for example. A lot of times when we have cold windows, people think that the window is leaky. The reality is that that window is a cold surface and our body temperature is moving to that window, making us cold and also making air drop down and flow across that window from the height of the window down to the bottom of the window, creating a current there. It doesn't necessarily mean that that current is connected to the outside. It's just this radiant energy that's happening there, or potentially the convection that's happening there. So the 6 variables of human comfort are things that we might or might not be able to control, from air temperature, relative humidity, air movement, and mean radiant temperature, to things that we definitely can control, which are the clothes that we wear. We might not be able to control our metabolic rate here, but we do have some ability to raise surface temperatures, to impact the relative humidity inside our houses, to limit the air movement inside our houses, and to, again, raise the surface temperature around us to better control comfort inside our houses so that people don't necessarily need to supplement their comfort in the house by putting on a sweater in the wintertime, as we had to do in the early 1900s that we showed before in those houses there. Thermal transmission is when all of these things are happening simultaneously inside of our houses here. So again, it's important to remember that conduction, convection, and radiant heat flow are happening simultaneously in our houses, but we can often figure out which is the largest trigger and concentrate on that. But really the synergy of how we control and gain control and predictability of thermal flow in our houses are having us look at conduction, convection, and radiant energy all at the same time there. Air sealing and insulation in the IECC relies primarily on manufactured instructions. There are some specific instructions in the prescriptive section that are actually mandatory for how you actually install insulation in floor assemblies or cavity, other wall assemblies or ceilings or attics. And then we have the insulation and air barrier table as well. But again, the code relies largely on manufactured instructions. So we need to understand how insulation works. And the reality is that insulation works exactly the same way that insulation works for our body. So this guy is wearing a fleece jacket. And the object of this fleece jacket is that it will trap a pocket of air. And it's really that stagnant pocket of air that creates the R value, or the resistance of flow of energy from higher concentrations to lower concentrations. So this energy is moving from this person's body to the ambient air outside of their thermal layer of insulation, which is this fleece jacket here. The problem is that that stagnant pocket of air won't remain stagnant if the wind starts blowing. If the wind starts blowing, then the air pocket is leaving the insulation, and with it, the energy is leaving there, and this person will become cold. So they need to put an air barrier over their thermal barrier. So we get a nylon shell over our thermal barrier here, and we have a system that ultimately works to trap a pocket of air and create an assembly, in essence, that works. So they've got an exterior air barrier, which is their nylon shell. They have their thermal barrier, which in this case would be fleece. And then they have an interior air barrier system, which would be their skin. They have a system that works exactly the same way that it works for our assembly. So we've got a thermal barrier here that resists conduction, but it doesn't necessarily resist airflow through that material. So we enclose our assembly on 6 sides with an air barrier system when we're talking about wall cavities and floor cavities in order to keep that stagnant pocket of air stagnant and get the R value of the rated R value of the material that's been installed. Because the reality is that insulation doesn't stop air movement there. So we need to understand, as we understand that, we can better look at the assemblies that we're building and try to better ensure that they're enclosed on 6 sides with complete air barrier systems, especially when we're using fibrous insulation in our houses. From an airflow perspective, we're going to change course here and start talking about airflow. And we need to think about airflow in our houses. I like to think about airflow as a freight train. Air is a transport mechanism, just like this freight train is a transport mechanism. This freight train's moving coal from point A to point B. Air is moving heat, energy, and pollutants around our houses. And the problem is, when does the train drop its load? Where does it put its cargo? So where does the air put its cargo? If it's putting heat and moisture inside of our cavities, that's a problem. We're going to get repeated wetting and condensation most likely from that. So we need to be able to control airflow so that we can control where it's depositing heat, moisture, and pollutants in our houses there. So you'll get this question quite often: can our houses be too tight? And the reality, the real answer to the question is no, our houses can't be too tight, because in order to control airflow in our houses, we have to be able to build a house tight. We're actually asking the wrong question here. We need to control the airflow in our houses, and to control the airflow in our houses, we need to build our houses as tight as we possibly can. But the real question is, are our houses underventilated? And the answer still, unfortunately, is yes, they are underventilated in most cases. We're getting better and better. It is now a code requirement that our houses not only be built tight at a minimum to 3 air changes per hour in most jurisdictions that haven't amended the code, and we have to couple that with ventilated houses, whole house controlled mechanical ventilation there as well. So if we can do that, if we can have the synergy of a tight house and a well-ventilated house, then we can live up to this mantra of building tight and ventilating right. It gives us the ability to have control and predictability of airflow in our houses and ultimately thermal flow in our houses and moisture flow as well. So we're looking for that control and that predictability in the same way that we're, might be going to McDonald's to get a Big Mac in Fort Collins or Windsor or Denver or Paris, France. Wherever I go and get that Big Mac, I know exactly what I'm going to get. I know exactly what it's going to taste like. I know exactly how I'm going to feel afterwards. That's what we're ultimately looking for here, is to get that level of control and predictability in our houses for airflow, moisture flow, and heat flow inside of our houses there. And ultimately, when we get that control and predictability, we're trying to get this equilibrium inside of our house, this balance inside of our houses that create this state of comfort inside of our houses. So to get that control and predictability of airflow, we need to be able to figure out holes and pressures inside of our houses. We have lots of holes in our houses. We're getting better and better at sealing up these different holes and places in our houses. The code requires us to do some of this. For example, here at the rim joist, the code requires this level of air sealing there. But the pressures are a little bit harder for us to do. So let's try to understand this in a little bit more depth here. If I have a rubber balloon and the rubber membrane of that balloon is my building thermal envelope, the alignment of my thermal layer and my air barrier system inside my houses, I have equal pressure on each side of that membrane there. The pressure pushing out and the pressure pushing in are equal. But if I untie the string and I create a hole, the pressures become unequal. I have greater pressure outside than I do inside, and I deflate that balloon. So in order for air to move inside our houses or around our houses, I need to have a pressure difference, and I need to have a hole that pressure can move through, that can push air through. And it turns out that we have some fairly constant pressures on our houses. We have stack, wind, and mechanical effect in our houses. But I need a hole as well for these pressures to interact and to move air through our building assemblies here. So stack effect or stack pressure describes what happens to air as it warms. As air warms, it tends to rise, or it does rise, and it hits the higher planes of our houses. And as it reaches the higher planes of our houses, in essence, it creates this positive pressure, and it's seeking a hole to the outside, maybe through a can light or plumbing stack or the connection between drywall and the top plate here. And once air leaves on the high side, it has to be replaced on the low side. So with this notion of air in equals air out, the same volume of air that's leaving the house is replaced by the same volume of air coming into their house. As our houses are taller, that stack effect can be increased. As the temperature outside, or the temperature difference between the inside and outside is greater, that stack effect can accentuate as well. But we're seeing these tall stacked townhouses being built, 3 or 4 story townhouses. It's pretty amazing, the stack effect that you can feel when you go up to the top level, put your head over the railing of the stairway, and you can feel the air coming up through that stairway there. And that's the stack effect that's happening. The next is wind. And I know it's not that windy in northern Colorado, but just say the wind blows occasionally in northern Colorado. That was a joke, and unfortunately it doesn't work well when I can't see everybody and interact with everybody. But anyway, air is is blowing against our houses, and it creates a windward side and a leeward side of our houses. And it creates pressures not only on the outside of our houses, but inside our house as well. So as the wind blows, we get a positive pressure on the windward side and we get a negative pressure on the leeward side of our house. And that creates a suction that is moving air from inside our house to outside our houses there. That can create a problem because that air potentially is moist and it's carrying heat. And if it's carrying that moisture and heat through our assembly, we can have a problem inside of our building assembly. Next, we have mechanical systems. Mechanical systems would be our HVAC systems or other fans that are moving air from inside our house to outside our houses that create unequal room pressures and house pressures there. So an example of that would be a duct system located in our attic that has a return side leak. The return side leak means that I'm returning less air than I'm supplying to the house, and therefore, because I'm supplying more air to the interior of that house, I'm blowing that house up like a balloon. I'm creating this positive pressure inside that house. The picture on the right is showing the reverse of that, where I have a hole on the supply side of my duct system, and therefore I'm supplying less air than I'm returning, and I'm creating this negative pressure in the house, and I'm sucking air from the outside into my home. Neither of these examples are good for our home. We obviously want a balanced HVAC system so that we're not creating pressures that are pushing air through our building envelope or sucking air through our building envelope there. Remember, air is a fluid, and it will move if there's a path present. So if there's a hole, that would be the path. And if there's a driving force, that would be the pressure. If those two things are present, then air will move through that building assembly there. If either are missing, air will not move. So we need this notion of air in equals air out is what we're looking at. Now we're measuring this in CFM or cubic feet per minute, air in versus air out. And to just conceptualize that, a cubic foot is about the size of a basketball there. So air is moving out 1 cubic foot, which would be 1 basketball moving out of the house. That means 1 basketball is moving back into our house as well. So we have this 110-year-old house. The question is why, how is it lasting so long? Well, the reality is that because it's drafty, because it's uncomfortable, it's also very durable because it ultimately has tremendous drying potentials there. If it gets wet, a lot of air is moving through that house and it's drying. But our expectations, again, have changed the way that we want to interact with our houses. And therefore, I've changed the drying potential of this house. And so because I've changed the drying potential of that house, I need to understand a little bit about how moisture is flowing through that house and how I promote drying mechanisms over wetting mechanisms in our houses. And this is the last part of what we'll be talking about today. So we know that things get wet, and therefore we need to let them dry. They get wet from the outside, from the inside, they get wet from the start. We often start with wet building materials. And then there's repeated wetting through condensation buildup in our houses and other sprinklers against the side of our houses, other things that happen that repeatedly wet our homes. Moisture flows this transport mechanism. It can happen by gravity, moisture draining down and out. It can happen by capillary action, diffusion, or vapor movement inside of our houses, and then condensation as well there. So all these things are happening there. What we ultimately are trying to understand is that vapor, water in its vapor state, and air are basically one. They are one and the same thing inside our houses. So air is that transport mechanism. Again, it's carrying things. It's carrying moisture and energy and other pollutants inside of our houses. So this is an example of an unbalanced HVAC system. Whenever you turned on the HVAC system in this house, it pressurized the house and it pushed air against this back door. And because this back door wasn't weather stripped well, air bypassed that door and it hit the security door here, screen door, and you see the condensation that was created on this door. This condensation can happen inside of our building assemblies as well. We tend to have a 1-inch square size hole every 6 to 8 feet around our house at our outlets there. So if air is being pushed through that outlet into our building assembly, we can potentially get condensation there. So just to summarize, we have holes and driving forces. If we can control the holes, we can limit the amount of moisture and air that's moving through those holes, because we need both the hole and the pressure in order for air to move through our building assemblies there. Okay, so let's talk about this table. Again, this table is helping us gain better control and predictability of the holes around our houses, so that we have less airflow through those holes and therefore less moisture flow through those holes. Relative humidity is one of the things that is a measurement of the vapor content inside of our houses. So this is the amount of moisture that's held by air compared to the maximum amount possible. When we have ultimate 100% saturation of air with moisture, then the moisture comes out of that air. So when we think about humidity, we need to think about the capacity of air to hold water vapor, and it's a function of temperature. So think about that temperature as a towel. The more that towel can absorb water, the difference in the relative humidity ultimately that we're going to get. Warm air can hold a lot more water, therefore we're going to have a bigger towel. We're going to have that bath sheet when we're talking about warm air. When we're talking about cold air, you're talking about the face cloth or the washcloth that you might have. Its ability to hold water is substantially less there than the warm air is. Absolute humidity is how much moisture is in the air by weight, and then relative humidity is the amount of water vapor present in air as expressed as a percentage of that total amount of saturation that can happen. So this is ultimately asking how absorbent is that towel there in the towel analogy here. Now, what's interesting that's happened most recently is that we're starting to understand relative humidity in a little bit different way in our houses from an occupant health perspective. So from a building perspective, the drier the air, the better. But from an occupant perspective, we're starting to learn that there's this sweet zone between 40 and 60% relative humidity that might actually help us decrease infection, prevent allergies, improve healing and hydration of our skin and whatnot. So there's this balance point that we need to reach, but what we ultimately know is that we can't go above 60% relative humidity in our houses, else we're going to potentially get mold growth in our houses. And ideally, we're going to be in that 40 to 50% relative humidity as a max, and below that, from a house perspective, that 20 to 40% relative humidity is where we want to be from a house durability perspective. But this whole COVID era that we're living in has brought up this new research that is kind of changing our thought process about relative humidity in our houses. And we need to figure out how we're ultimately going to deal with that and continue to have houses that are durable over time, but also meet our occupants' health needs as well. From a moisture control perspective, we're trying to ensure that we're not getting mold growth in our houses. Mold is always there. But mold needs some things to help it grow. It needs that wood or that nutrient to be able to help it grow. But it can grow on all kinds of different things, from drywall to carpet fibers to upholstery to paints. It can grow on all those different surfaces there. But it ultimately needs the spore itself, its nutrient, its moisture content in order for it to grow properly. And if we can control mold growth, it means that we need to control moisture and keep it in that relative humidity range of 30 to 50% relative humidity. We need to stop condensation or that repeated wetting that would help mold grow. And we need to have better air control in our houses and ventilation in our houses to control the spores and whatnot that are in our houses. And ultimately promote drying mechanisms over wetting mechanisms here. So we have these different ways that moisture flows in our houses, from bulk water to condensation. Bulk water is ultimately thinking about how do we allow water to hit the surfaces of our houses, to drain down, and then ultimately away from our houses using gravity here. So we want to direct that water down, out, and away from our house using gravity. And that's our primary systems for doing that beyond our roof assembly is these drainage planes, drainage screens that we install in our houses, a variety of different products out there to do that. But what we're learning really is that we not only need to put these features on our houses, but we need to also introduce a gap, a drainage gap in our houses to promote that ability for the water to drain down and ultimately away from our houses. So this vented rain screen is what you're going to start hearing about more and more there. Capillary action is when water is sucked upward through the pores of porous concrete, for example, in this situation here. And these tiny pores create this capillary suction that moves the water up and out. So capillary breaks are things that will stop that moisture from moving from one component to another component. So sill seal is actually a capillary break to keep moisture from moving from our concrete up into our wood assemblies here. There. It does not work very well as an air sealing mechanism because the top of our foundations are not very level, and we tend to shim that sill plate a lot. So the code is actually asking us to air seal this connection as well as get the capillary break in there. But the primary focus is capillary break. And then if we're really looking at the applied building science, we're going to start thinking about how do we get capillary breaks between our stem wall and our footings, and between our slabs and the soil below our slabs, because that soil has a constant moisture content that's trying to wick up into our building assemblies there. And we want to obviously keep it out of the wood component there. Moisture diffusion is when moisture is moving from higher concentrations to lower concentrations there. And it's moving directly through the pores of our assemblies. Now, the reality is that this moisture movement is a rather small moisture transport mechanism. Diffusion, in this study that's been done over and over again, we have a sheet of drywall, and over the course of a heating season with the conditions that are demonstrated on the slide, only 1/3 of a quart of water was able to diffuse through that sheet of drywall, whereas 30 quarts of water were able to move by air leakage through a 1-inch square hole in that assembly there. So it turns out that the code is really focusing heavily on diffusion and has just recently started focusing heavily on air leakage. But air leakage has been focused on from an energy perspective, not necessarily from a moisture transport mechanism. And we still have some work to do from a building science perspective and the code to link moisture transport and air transport together there from a code perspective. Because ultimately what we're trying to avoid is moisture buildup in our assemblies that create condensation on that first condensing surface here. So this diagram shows moisture that's moving into the assembly by the process of diffusion. Remember that that's a relatively small moisture transport mechanism. If I have a hole in that assembly, I'm going to get way more moisture through that hole than is able to diffuse through the assembly. But in either case, that moisture that's in that assembly has the potential to condense on that exterior sheathing if that sheathing is at a particular temperature. The dew point temperature is what we're ultimately trying to avoid. The dew point temperature is described by a thing called a cyclometric chart. This is a abbreviated or simplified cyclometric chart that shows us if I have 35% relative humidity in 70-degree air and it hits a surface temperature that's 40, then the moisture is going to come out of that air and into a moisture droplet that is the repeated wetting of our assemblies there. And that repeated wetting is condensation. It's the most common form of moisture that's encountered by buildings, and that's why the code is asking us to do insulated corners and insulated headers so that we warm those surfaces. And in our climates, we have options in climate zone 5 of doing insulated sheathings to warm that surface temperature. And as we move up into the mountains, it becomes really almost a requirement to start putting foam sheathing on the outside to reduce condensation that might happen inside those assemblies here. Tight houses have higher levels of humidity just by themselves. So we need that background moisture control through ventilation here. We also need source control through ventilation to ensure that what we're doing in our kitchens, bathrooms, and laundries, that moisture is taken up and out of our houses as soon as it's created. Because we have this great assembly here, but if we allow moisture to get into that assembly, the way that the code is asking us to build that assembly right now by putting a vapor retarder in the assembly, that vapor retarder is likely to actually trap moisture in that assembly. Because ultimately, we don't install the vapor retarders in Colorado very well. We don't overlap the seams. We don't put airtight boxes with flanges on them. We don't seal the vapor retarder to our top plates and our bottom plates and to our other openings. And we don't even put the vapor retarder continuously around our building envelope. When's the last time you've seen a vapor retarder at the rim joist, for example? It can be problems here. Condensation resistance factor. This is an interesting new label or new component of the NFRC window label that's come out there. And it's something that we should be looking for. Basically, the warmer the window's surface temperature, the less condensation we're going to get on that window. So again, the continuity of our air barrier system to keep moisture out of the assembly, and then ultimately ensuring that we have drying mechanisms over wetting mechanisms, that we avoid vapor barriers when retarders will work. We avoid vapor retarders where vapor permeable materials will work in our assemblies, and we avoid the installation of vapor retarders or barriers on both sides of our assemblies. We don't install vinyl wall coverings. This is generally more often an issue for motels and hotels and whatnot than housing, but it can cause problems. We have proper ventilation in our assemblies there, and we make sure that ultimately we're allowed and continue to use class 3 vapor retarders over class 1 vapor retarders. There's some ability for our assemblies to have drying potential there. Okay, to conclude, so I don't keep you too long, we need this understanding of building science, again, revolves around the notion of systems thinking, that idea of synergy, 2 or more things coming together to achieve something that they couldn't achieve before. Applied building science is being wrapped into the code more and more so that we get control and predictability of heat flow, airflow, and moisture flow in our houses. This sound and well-defined building thermal envelope is the key to it, so that we have insulation and air barrier systems all the way around our houses to help us gain that control and predictability. We see that the IECC and the IRC and other building programs out there like Energy Star and the DOE Zero Energy Ready Home program, they are incorporating building science into their programs and into their codes. And the better we understand that building science, the better we can integrate it into our building process if we start from the beginning and start early in the design process of our homes. So thank you so much for taking part in our series and this session today. If you have any questions, I will hang out and we will talk about those questions. If you also like to reach out to me directly, feel free to reach out to me directly and we can talk about them as well. So there are a couple questions here. Joe Madash, how are you doing? It says we rarely have 40% relative humidity inside our houses. That's true here in Colorado. In other places around the country, sometimes we get that high humidity. We also see some people, especially people that are coming from out of state, that install humidifiers in their HVAC systems that are pushing the relative humidity pretty high in our houses. The question is, can you elaborate on the location of the vapor barrier? Some people actually install a sheet of plastic on the interior before they put up the drywall. Great comment, Joe. Unfortunately, the way that the code is written, it mandates a class 1 or class 2 vapor retarder in climate zones 5, 6, 7, and 8 there, unless you put foam sheathing on the outside and or a air gap behind a vented rain screen, in essence, behind your siding on the outside. If you do foam sheathing or a vented rain screen, you're allowed to use a class 3 vapor retarder, which would be paint on your drywall, in essence, there, which gives you a much more forgiving assembly, an assembly that has drying potential in both directions. That's the assembly that we really want, and we want to promote. So there are some jurisdictions that are allowing you to move away from plastic in your assemblies. It's not consistent up and down the Front Range. The city of Denver, for example, has started to default back to class 1 and 2 vapor retarders. Douglas County will allow you to do a variance to get out of it. I believe this question, Joe is actually asking you, Brad, if in Fort Collins, you'll allow people to design assemblies without a class 1 vapor retarder in it. So if you want to jump on and answer that, that would be great. Colorado Springs, for example, has eliminated the requirement for a vapor retarder in their jurisdiction. So you definitely need to ask that question and think about it hard during the design phase of your project so that we're not getting assemblies that are trapping moisture inside of them. I'm not sure if Brad can jump back on here, but I'm pretty sure that Fort Collins will work with you and allow you not to default to a class 1 vapor retarder. There's Brad. Brad, you're muted. Brad, you're muted.
There. Thanks. Yeah, it has been part of the discussion at the building department, and we are in a position where we are not enforcing it at this point. We certainly will allow it if we see it in a building and it's installed. They're not going to say anything about it, but if it's not installed, the building department staff is not going to fail the building.
Great. Does anyone else have a question? Okay, well, I'll continue to hang out for a few seconds. The HBA has recorded this assembly and this presentation, and it will be posted on their website, and I believe also the Fort Collins website. So you can go back to it if you have any questions, and please don't hesitate to reach out to me if you have questions or would like to talk about anything. And Brad is available. He's a building science wizard as well. Okay, well, thanks so much for your time. I think we're going to sign off. We'll see you next Friday.